Yeah, so hi. So, what I was saying, week 9 is quite straightforward because if you look at the mutation operators, so mutation testing, we do some simple change in your code and try to find out if your output is different from which program, the program, like actual program and the mutated program, right? If they're different or they're same, this kind of thing. So there are some concept of infections and all. So often maybe you can discuss those part, that infection and propagation, that part. So that's a conceptual part. But other than like the kind of mutations, right? Those are very straightforward, like arithmetic kind of mutation. Like for plus a plus b statement is there, you make it a minus b, then you make it a multiplied b. So these are the changes you do. So scalar means like if you have a plus b, you'll do a plus minus of b, that kind of scalar mutations. It's straightforward quite if you just go through once. But if you look at week 10, so I'll suggest everybody like do whenever you are studying, try to find out some relation with the inheritance, polymorphism. Those are the concept you read in Java. Because if you cannot relate with the actual code, because ma'am didn't use lot of code over there, she has discussed mostly concept and some class diagrams over there, right? So class diagrams are basically very helpful, but if you write some kind of code, so that will be extremely helpful. And I'll suggest for old paper also. So if you look at the assignments, the questions again are not so complicated, but old papers, if you look at, the questions are bit complicated because it's what are the mutation operators are there, they're converted into a program and then the question is asked. So some kind of relation you have to establish, what the theory you're reading and what the code is. So I'll suggest for week 10, whenever you're studying it, keep the old papers with you and try to follow that questions and try to relate that questions uh, with the topics you're studying, right? So maybe Afnan, you can start with that part. Week 9, like what is the mutation testing and what is infection propagation, that part
Hmm.
maybe. Otherwise, that operators are quite straightforward. I think everybody can understand. If somebody having some problem, we can discuss it later.
Sure, sure. All right.
Okay, Afnan, you can start.
All right, sure. Thank you, sir. Just give me one moment. I'll share my screen. Continue with that. All right. Please let me know if the screen is visible.
Yeah, it's visible.
All right. Thank you. So this is regarding mutation testing, which is coming up in week 9. So before going to mutation testing itself, we'll discuss briefly about syntax-based testing in general and regular expressions, right? And how are they useful, and how these compilers are actually doing the job of, translating code into machine code, because there has to be syntax, right? Because if you write code, a particular programming language, let's say in Java, then there is a specific syntax which you must be following, right? Then only your source code is considered grammatically valid or syntactically valid, and then only it can compile, right? And then you can run it, right? So herein we are doing syntax based testing, as in doing testing using the, you know knowledge about the grammatical aspects of the programming language that is under use, right? So I mean, there are only, if you think about it, there are only a limited set of possibilities that can arise if you have expression. Let's say, for example, I have one method, so I'm just giving an example, very rough example here. So I have a method, right? In that I'm doing some calculation, right? So I mean, there are a limited set of arithmetic operations that you can use on that, right? So assuming that there are variables, let's say a and b, then you might perhaps do a plus b, a minus b, a into b. There are a finite set of operators. Is what is available with you, right? In that particular situation, right? So that is why what we try to do in syntax based testing is that, whatever code has been already given to us, we try to make some changes by way of what is called mutation. So we mutate the source code of the program and then run it, and then we compare whether it is you know uh, uh, producing the expected output or not. So that is what we do in general, but we'll go through it and we'll see what happens. So there's a slight distinction, from the previous testing paradigms that we have seen. In this, we are making changes to the source code itself, which was given to us. That was something that we have not done so far, no, in the techniques that we have learned. So that is what we have. So this is regarding the syntax-based testing itself. And after this, this is like a prerequisite. Once that is over, then we'll go to uh, mutation testing, and discuss that in detail if possible. To understand that, it is important to understand this one as well. So what do we do is given here, syntax based testing. So we consider the syntax of the software artifact. That's okay. So there is this notion of a syntax, which to us might be familiar, but we are trying to, formally state what it is. Okay. So it says can be used to generate. Now artifact here, most in most of the cases, at least for this discussion, is going to be source code only, right? But there can be other kinds of artifacts, and therefore we are not using the word source code in the introduction. However, our discussion is mostly going to be pertaining to the source code of the program itself. So thereby, you can assume artifact to be the source code itself. That is one side note that I wanted to mention. Okay. So that is what. So it says syntax can be used to generate artifacts that are valid and those that are invalid, right? So both syntax, be like whenever you write something, let's say you write something in the programming language, right? So there can be two kinds of things that can come up, right? One is the valid code, as in syntactically valid code. So the compiler won't generate any error, and you'll be able to successfully compile that. Now, whether or not that program works as intended or is not, or is something different, because that is what we've been doing earlier. So we run the program, and then we are interested in what is called runtime error. Okay, so we are trying to find out if the program is running, then is it behaving as expected or not, or are the outputs as expected or not. So that was the earlier techniques. In this case, we are doing it on syntax itself, right? So we are trying to understand whether the source code of the program is syntactically valid or not. That is one. And using that knowledge, then about the grammar of the program itself, we'll see what grammars are, right? And then we are trying to see like amongst those possibilities that are valid, as in syntactically valid, those possibilities which can compile, right? When we make a change, we make a mutation, we change the source code, but we have to make sure that it still compiles. Because otherwise, if you have something, if you have a source code, you make a change so that it is not compiling even, then there is no question of testing, right? You have to have something which compiles first of all, right? So you make changes so that they are valid also, in the sense that they can compile, and then you test on that. So that is something that we will see. But here it says that in general, syntax can be used to generate both valid and invalid artifacts, as in syntactically valid and syntactically invalid. So let's say a famous example might be of Java, wherein if you miss the semicolon at the end of the line, right, then it says that it is not a correct syntax, and therefore it will not be able to compile your program. So that is one very basic example that we might as well relate to. Okay, so that is what syntax means. And okay, the structures artifact that we generate are sometimes test cases, but most of the time they are not. They are used to generate test cases. What it says is that uh, by by means of this mutation that we are going to do over source code, right? That itself won't be a test case as such, right? So what you will most often than not end up is that is going to be a source code again, which is a mutated version. So herein we call it a mutated program. So there was this actual program, actual source code, which was given to you. You make a change to it, so you get a new program, right? I mean, the source code would be different, right? But that is again a source code, and then that on that you test, right? But and we'll see how do we test on that, and that is what it says. So the artifacts that are being generated are not test cases, right? Sometimes they can be test cases, but most of the time they are not. They are another source code. They are another piece of source code which again you run and then you test on that. So that is something one must keep in mind. So the coverage criteria is something like that. So one first thing is like there are, so in syntax based testing there are various criteria that are there. So for example, in the earlier cases also we have seen that, let's say we have graph coverage criteria, and then we have symbolic execution and the respective coverage criteria for that, and so on and so forth. Similarly, syntax based testing also can be of various kinds, and therefore they have their own criteria which we must fulfill, right? So that is what it says. So one thing is coverage criteria based on grammars and regular expressions that we're going to mostly see in today's class, right? And then comes mutation testing, as in we make a change and then we test on that. So that is something that is like a application of what we're seeing here in syntax based testing. And then we mutation testing applied to other kinds of things also, like for example to source code. Yeah, I mean, like usually the artifact is going to be source code. That is what you're going to test, but it could as well be other things, like for example design elements or xml code or something else, right? So that is because you're everywhere you have a syntax, right? You can think about it like that. So wherever you have a syntax, you can make changes, no, and generate valid and invalid artifacts, and then perhaps test on that. So that is what mutation is about. All right. So we're talking about programming language syntax here and what it involves briefly. So it says the syntax of the programming language is given in three levels. Okay. So the first thing is words, something called words. These are kind of parts of what a syntax is. Like a syntax is a constituent of all these things, right? So the word is like the lexical level, and it defines how the characters are forming tokens, as in what keywords, for example, would be valid. Let's say if you write do, right? do. So that is a valid keyword, right? In let's say Java, for example, or while loop, right? So while, right? These are spellings, right? Which are valid, which are not valid, and all that. Because in other programming languages, you see other kind of conventions, right? So for example, in Bash and other kind of scripting languages in Linux, you see if and end if and all those things, right? Whereas in Java, you won't see end if, for example, right? So for to end the if block, you have to use braces, right? So all these things are like the lexical level. What constitutes valid words, right? So that is like the unit. And then these words from the phrases, something known as phrases. So this is at the grammar level, and then it determines how tokens. So these are like, we're building upon that. So once we had these lexical levels characters, right? From those characters we form tokens, and then those tokens in turn are forming phrases. Okay. So these grammars, these phrases are basically specified using the a Backus nor form is something that is BNF. So we'll see what it is. Okay. And then again, so in syntax, words and phrases are there, and then context is also one more important thing. Okay. So it deals with types of variables, right? So for example, again, the same thing, like for example, if you have a string variable, let's say strongly typed language you have, let's say Java, in that you write let's say string a is equal to 0, right? Then it will complain saying that you cannot assign 0 to a string, right? But that has to be an integer and all that. So this context is something that that is there, right? You have to have an understanding of what is allowed and what is not allowed and all that. So these are the three constraints that are being discussed here in the syntax. There might be other things. You must keep in mind that there might be other things to a syntax of the programming language. However, for our discussion, we are seeing these things only. Okay. So uh, the kind of the core part of how these things work is by means of regular expressions. So one might have heard it in the earlier courses on Linux, for example, in system commands and other such courses, wherein we used to work with regular expressions and utilities such as grep, right? So grep is one such utility wherein you can do search based on regular expressions and so on and so forth. So all these things, internally, what constitutes valid syntax or not, and how to make a programming language so that it adheres to a specific syntax is so the kind of the engine to satisfy all these constraints is regular expression, right? So it is the language. It kind of allows you to define a semantic for your language. Okay. So there are few operators in regular expressions that we'll see here that is being discussed. So we are talking about an alphabet. So an alphabet is a collection of possible characters that you can have. Okay, so think about it that way. Okay, so let's say if I define my alphabet to be a comma b comma c, that is a set, basically a set of valid characters. Simply. So if you have a comma b comma c, in that case only these characters are part of your alphabet, and only those will be valid, right? So what a regular expression then is, we are defining a regular expression. It says it could be an empty set, as in even if you don't have anything, that is still a regular expression. So that is like the base case. Okay. Then you can have the alphabet itself. From the alphabet you take something, take one character for example, and that is it. It is also a regular expression even if you don't do anything on that. Okay. And then there is this plus operator. Okay, which so I think this is concatenation, right? Yeah, this is concatenation. So the plus is a unification operator, where what it says is that if you have another regular expression, then you do a or. So it's like an or operator. Okay, this or that. So it is like r plus r, right? Similarly, you can see here what happens to the semantics. We'll go to that, but just understand the operators first. So there's this plus operator, and this dot denotes concatenation. Okay, so like for example, if you have two strings and you concatenate them together, then that is what this dot signifies. Okay. And then you know you have a r star. I'm not able to recall what r star does. Okay, r star is repetition. Okay. So r star says zero or more than zero repetitions of whatever regular expression you had. So for example, and you can see that this is kind of a recursive definition, right? So whatever you get is forming a closed set. So after you do that operation, you again get back another regular expression. You can continue doing that. That is how we build up. So if you have two characters, then I say a dot b, that gives us ab, right? And then I do a asterisk over that. So it says any repetition of zero or more repetitions of ab. Okay, so that is how we define it, right? So star denotes zero or more than zero repetitions. And then there are semantics that are associated with those regular expressions. It says that if it is an empty set, then as I described, it is going to be empty, so nothing is there. Whatever will match, basically we'll see what matching is, right? How matching works. So if you have empty set, then that is like blank. And then if you just have one character from your alphabet, then that is going to match only that, right? And then you have this r plus r prime. Then you have whatever L of r is union with L of r prime, right? So it depends. So you kind of keep adding to whatever possibilities are there, okay, to match the set of characters. And then you have this concatenation also. So it says concatenation of r dot r prime is going to be uh sorry, L of r dot r prime is going to be L of r dot L of r prime. So I mean, like, these are associative things, so we can do it separately also. And then L of r star is going to be L of r star, so that's okay. We'll see how it works now. So these are examples. It might make it more clear. So it says expressions built from a, b, and epsilon. Okay, I think epsilon is denoting the empty set if I recall correctly, but we'll see what it does. And the operators are this again as I described. So plus is unify, this is concatenation, and this is a repetition, star. So you can see how to read this now. It says a star plus b star and concatenated with c. So it says strings of only a's or only b's. So that is why I said this is like an or operator, right? So any number of a's or any number of b's, and then finally ending with a c is what this regular expression is trying to say. Okay, so we have to be very uh, you know careful while reading this and understand it properly. So you have to practice a little bit and then kind of make it a habit to understand it quickly. right? What a regular expression is trying to say. It might take some time, initially, but as and when you practice, you'll be able to get it. Because then only you'll be able to generate the tree for it, and then understand how it is working. But that is how it works. So again, one more example. So it says a or b any number of times, this part, followed by, and if you have nothing, then it is assumed to be concatenation, similar to how repetition works in mathematics, right? So if you don't have anything, then you assume it to be product. Similarly, here if we don't have anything, then we assume it to be directly a concatenation. So it says basically that I want a string such that it starts with a or b any number of, and that is repeating any number of times, right? And then you follow it with a b b, and then you again follow it with a or b any number of times, right? So basically what it says, if you think about it, is that any string, because you remember that we only have a b in our alphabet, right? So therefore if we say any string, which means any string which could be formed from those alphabets, right? So the meaning of any here is going to be limited to whatever alphabets we have available, right? So it basically says from our grammar, any word that could be formed such that it contains the subword ABB is going to be matched with this, because again you can think about it, right? In your alphabet you only can have A or B, right? And that could repeat any number of times, and remember that it also contains zero. So if I say A plus B 0, basically that means it is not there. Zero repetitions means it is not there at all, right? So it might as well match the string ABB itself standalone, right? So that will match. However, in general that is going to be a subword, right? So anything before that, anything after that, and I need ABB in between. Okay, so that is how it is defined. In this case I think it is different. The description of it is not given here. Yeah, here it is. So yes, this I described. This one is again okay. Yeah, this one says any number of times A or B, okay, and then followed by a B. Then pay attention that this does not contain the asterisk. Okay, so this is only uh, one character. Okay, so B, and then after B I need A or B, and then after that again A or B. Okay, so basically it says strings where the third last letter is a B, because you're fixing B here, right? And the last letter could be A or B, the second last could be A or B, the third last must be B, and before that you can have A or B any number of times repeated, right? So you can think about what possible strings are that it could match. Okay, so pay attention to this. And again, so this one, the last one I believe. So it says strings of B's that optionally begin and end with an A. That is because you have a star, so it also it could be zero also, and therefore it says optionally, because if it is zero, I say zero repetition, so it means that it is not there. So it might not as well begin with an A, but it could optionally begin with an A and then also end with that. Okay, and then and followed by a string of zero or more B's. This part, B star, B star is what we have. I'm sorry, I'm not able to select this portion only for some reason. But what I mean to say is that this B star, the last one, means that zero or more B's. Okay, so you can see that this is all built up using the semantics that we described earlier and the syntax and the operators that we had, right? So we are kind of doing these operations while defining the regular expressions, and similarly we are getting more complex regular expressions out of them. That therefore I said that this is a recursive definition. Whatever you do on a regular expression, from amongst these sorry from amongst these operations, you're going to get back a regular expression again. So it is going to be the same thing. Okay, and then again you can keep doing it, right? So that is a recursive thing. So these were the examples. Before going on to the next slide, I like to take questions if there are any at this point. If not, then please let me know. I will go forward.
Um, Afnan, the last one, the
Yeah,
AB star A.
yeah.
So why does it say that? In fact, the A B star A, the ones in bracket,
Hmm.
that's actually optional, isn't it? The entire thing is optional.
Yes, that's correct.
So why does it say strings of B's that optionally begin and end with A? Because the string of B itself is optional,
Yeah, that is correct.
right?
So
Yeah.
okay, I get your point. So I think Anand, the point is that if I make everything zero right here, I get your point totally. So the first thing is like in parentheses, and that is like a star after that. So assuming that this star means zero repetition. let's say,
Yeah, right. Yeah.
for the sake of this argument, and then I also say that this b star also means zero repetitions of b, then I basically end up with an empty set that is phi, right? So that will.
I'll just have, and
Hmm.
basically it points only to zero or more Bs. Yeah. In fact, it can be completely empty,
Yeah,
or it can enter with, I mean, it can just have a string of zero or more Bs.
yeah, that is also possible, and the other possibility is that it could as well start with this
Yeah.
prefix, whatever prefix regular
Okay.
expression we have, right? So
Okay.
three possibilities. So it says this b that is referring to in the next line is basically referring to the last this one, this part. Okay, so it says in general that is going to be a strings of b. So we are here assuming that b is not going to be zero, like this. The last b repetition is not going to be zero, and therefore we are assuming that.
No,
And
that
then
last part is indicated by the second part of it, followed by a string of, that is what indicates the last B.
okay. So okay, yeah, yeah. I think
I think they are not considering this after parenthesis this star.
oh, this
So,
star is what I think they are talking about.
this
So
star
fine,
is
right?
extra. I
Oh,
think.
okay, okay,
All
okay.
right.
Outside the parenthesis, one extra star. I think that won't be there.
Oh, is it sir? All right. Okay.
I think so.
Okay.
Otherwise, what Anand is saying, that's true.
That's
It
true.
could
That's
be
true.
null.
Hmm. Hmm. Because it says optionally begin with and end with an A, and A is only present here in the first thing itself, within the parentheses, right? And then we are following it up with the string of zero or more b's.
Right.
Okay, so this is again zero, right? So basically, this star is counted. Yeah, but in between these two things, there is this star about which we are not sure.
Yeah,
Okay.
that's okay. We can go ahead.
Yeah,
Yeah,
we will see that.
no
I
problem.
think if we decompose that into a tree, we'll be able to make sense of what it means. Okay. All right. So what it says basically, once you have this expression, is that you can basically construct a tree using the semantics of the regular expression, and that is what we're doing here. So this will allow you to understand how these tokens. Now I'm borrowing a word from there, which we described in the introduction slide, and that how these tokens are basically going to form different words, and therefore we also check by means of these semantics whether something is valid or invalid. Remember that we were talking about something, the syntax being valid or invalid. So before going there, before being able to judge whether something is constituting an invalid syntax or a valid syntax. So let's say you're designing a compiler. That compiler is going to uh, translate your code for some programming language into a machine code. Then the compiler must understand the semantics of the syntax of your programming language, or the programming language that compiler is going to work with, right? Then only it will be able to do that. So therefore we need something formal, right? Some formal notation, or some formal way by which we can parse these things. Okay, so here this term parsing is coming in. What it means to parse is basically, if you have something written, right, uh, to extract semantics. I mean, that is how I put it. I mean, like, you can look up what parsing means. So if a JSON string, right, let's say in APIs also, recall that we used to send responses from the server to the client, and then the client used to parse the JSON object that used to come in, and then only you used to work with that, right? So that payload that came in the HTTP request, slight digression here, but I just wanted to make a point. So that payload that came in from the server to the client was a string, actually, because HTTP, recall, is a string based protocol. So that sends us a string, and then the JavaScript basically it translates it back to object, JavaScript object, right? And then only you work with that, right? So that is what, or recall, if we've been there, I don't know, in Java, in serialization and deserialization, that happens, right? So if you want to save something to a file, an object, then you serialize it to some binary format, and that is saved to disk, and then you deserialize it. So what deserialization does is that basically parses it back to an object, right? So that is how. So once we have this regular expressions, we need a way to parse these, or a way to extract the semantics out of these expressions. Then only you'll be able to understand the structural the structure of it, and then you'll be in a position to decide whether something is part of a valid syntax for you or not, right? So the syntax itself is up to you. That's okay. I mean, whatever language you're going to come up with, using these things is up to you, whatever semantics you define for yourself. Like what is valid or what is invalid is up to you, because other several programming languages exist, and each have their own way of describing things, right? So that's okay, but something has to be formal so that you can work with that, right? There has to be a way. So that is what regular expressions are providing you with. So here what it is doing is that once we have the syntax, and this thing is like common, right? I mean, we kind of construct the tree and then we do the parsing. So that is common across every programming language that you see. Okay, so this is this is the thing that is working under the hood to make the compilers or the interpreters understand code, you know, of various programming languages that are out there. So okay, so how it works is that it's a very basic example of just building the tree here. So at the bottommost level we have A, B, and C. These were the characters that we had initially, right? And then we did this part that we had a star with A associated with A, so that is like a parent, parent-child relationship. So this is like a tree, right? So here we have A, and that is going to this one, and this B is again going to this star. I hope my highlights are visible. And then once we have this, so recall that I said every operation that you perform, you again going to get back a regular expression. Yeah, that was a recursive definition. So again I can apply, right? So once we have A star, and this side we have A star, this side we have B star, and then we do a plus on that. So we get A star plus B star, and that is the first part of it, right? And this is how you read it. And then you had a C separately here, and then you're doing a concatenation on that. So you had A star plus B star, and then you concatenated with C, and that is how. So at the root of it, you get this whole thing. This is how you define it. So you break it up. Okay. So first of all, at the topmost level, you're going to have this concatenation because you have that is what you have, or you can start with the bottommost level also. So start with these characters that we have, and then apply operations on them. So A star again, B star plus, and then we are doing out of this left side we get another regular expression. Out of the right side we get another regular expression. So we do a plus on that. So you get A star plus B star, and then we could do a concatenation on that with C. So we get A star plus B star dot C. So this is how a tree looks like. Now see how the parsing is going on. So this part is the tree itself. Okay, so recall that these were all sets, right? So it says the thing that is going to match it is basically this set A, because at this level you don't have anything, no operations, like this is at the unit level. So we just have A, here we have B, and here we have C, right? So that's okay. Now we'll go level by level. In the next level you do an star operation, and that basically says what are all the possibilities then you have, right? So it goes on. And recall that you also have epsilon. Epsilon was denoting the empty set, nothing is matched, because we say 0 or more, right? So then once you apply the star operation on that or repetition, basically you get this set. Like it can be empty, nothing is there, or 1A or 2A's, and so on and so forth. So it keeps on going at this level, at this star. Okay. Similarly for B, we can have epsilon B or B, and you can just go on, So this is just repetition. And then you are doing, and so we'll go to the other level also. So these were the two levels. We go one level up, we get this. Now see what are the possibilities. Let me just zoom it in a little bit. Yeah, here. So we can have, now we had these two sets, so these are all other sets. We do a union of these things, and then we get empty, because empty was anywhere there. So we do a union, we get that A B or A, right? And so on and so forth, all such possible things, right? So this is A star plus B star. Sorry, yeah, A star plus B star. So this is how we get at this level. Okay. So C is not there. Note that at this level we don't have C. C is only coming after we concatenate. So we'll see what happens. Okay, and then we do a final concatenation. Recall that since we are doing this concatenation with C, even empty sets. So even if this A star is 0, let's get empty set. So and then empty or empty is going to be empty again. And then we concatenate with C. Therefore, epsilon is going away here. Epsilon is not here. So either you're going to have one single C also, or AC or BC or AAC or BBC. So whatever you had at this level, no, you're just concatenating with C, everything. So you get these possibilities. So the final thing is what constitutes the set of possible matches, or the set of valid strings for this particular regular expression that it will match actually. So I hope this part is clear. Any questions at this point?
No, no.
All right, thank you. So
Uh,
go. Yeah.
is it possible to? I'm sorry. Is it possible to also look at the mutation testing today?
Yeah.
Maybe we can. Maybe we can cut down a little on this,
Oh
and
yeah, sure.
can we
If you wish.
focus on that?
Yeah, yeah. All right. Oh, if you want to do that, we can do that. So, all right. So this was the discussion about regular expressions only. So recall if we go back quickly, since there is this request. I just try to quickly summarize this. So what it says is that this was about regular expressions, right? I mean, and regular expressions is like, I think that was the last slide describing regular expressions. And using these, we are going to work on context-free grammars also. So this context-free grammars is is something that we can perhaps discuss at a later point also, if you want to go to mutation testing first. So this was the general idea about regular expressions. If needed, we'll come back to this and see context-free grammars. We were hoping to actually cover this one also, because if context-free grammars are clear, then a lot of things you'll be able to relate to what is coming up next.
Okay. Okay. In that case, fine. I was just suggesting
Yeah,
that's fine. Let's go ahead with this. No
yeah.
problem.
I'll try to brief with
No,
this.
because when sir Harup sir talked about it can it can be difficult when you look at the code and do the mute. I was very curious to see an example, and
Right.
that's why. So I didn't want to miss out any discussions on that.
Yeah, yeah, surely. No, no, definitely. So I will just quickly go through that, because it'll be recorded, so it'll be kept in the video also. So
Okay.
for others also, it will serve as a reference for the mutation testing part. Because it will take time, I just want all of you to appreciate it, that part. Like, mutation testing is what you're going to get questions on going forward, right? I mean, there will be questions on context-free grammars in general also. You might be seeing regular expression questions also, maybe, possibly, but not so much. CFG is what you're going to get mostly, in the assignments also. And then, of course, mutation testing itself is what is going to be the culmination in some sense of all of this. Okay, so that is what we'll see. But yeah, so we'll just quickly go over that too. So what context-free grammar says is that there is no associated context with that. So whatever input you have, you just keep on deriving. So there is this derivation that happens. Okay, of new strings. We talked about grammars, but like, we talked about regular expressions, so that is one way. But then again, grammars define how do you, like, given some string that is there, how do you go to next string. So there are rules. Grammars are basically rules of from one. Think of it as graphs. Okay, so if you are at a node, then what are the possible paths that you can take, wherever you can go from that, no possibilities. So grammars are basically defining the rules of production of strings. So it is it'll be better if you understand this, so we'll just quickly go over that. So it says, there's one example of the grammar. So the rules are given here. You start with s. Okay, so that is like convention, begin with s. And it says where you can go from s. So from s you can go to ax. So what we do is we just replace it. We replace s with ax. This is very easy to understand. Okay, ax. And then, so a remains, because a is that is like a literal, right? So it is there. It will not change. Whatever is variable, only then that you can change. So you have x. So from x you can go to three other possibilities are there, right? So you can again go to ax. So what will happen? You get AAX, right? Because you replace X with the next one, whatever it is. Or you can go to BX also. So what do you get? ABX. Or you can go to directly to B. But if you go to B here, the third rule, by using the third rule here, or the fourth rule rather, right? So you get AB, and that will end in a terminal string is what we call it. So non-terminal is, these things are non-terminal, because you see a variable is there, X is there, right? So you can replace. There are further derivations that are possible, is what this is saying, right? But if you end up here, that is going to be a terminal string, right? So once you end up at a terminal, then further derivations are not possible. Okay, so you have this s, right? So we are generating. So from s we go to x, and this is just so from s anyway we don't have any other choice, so we go to x. That's okay. But here onwards, whatever we choose is just a choice. Okay, so once we have x, no, we can either go to ax or bx or b, and you can see that based on what you select here, from the choices, you're going to get a different string here, right? So if I had selected from ax, again ax, this one, the second one, then I would have got aax. However, Since I selected this bx, I am getting to a bx, right, and so on. So if I select the last one now, I get to ABB, and that is one string. So this is another way of coming up with new strings. So we'll see. All right. Again,
So
yeah,
I
go on.
have a small doubt. Does the language generated finally changes if we mix the order up? Like, if, for example, if I start with S implies AX and
Mhm.
then go to X implies BX and then move to X implies AX, then will the final language generated change,
Yeah,
or
I
will
mean the
it
language won't, I think, change, because the language constitute. I mean, like the language is the grammar itself, as in what are the possible strings that you can generate. But if you do derivation, what you're saying is that you are deriving strings on that. So if you in derivation, the order matters, is what I'm saying. So for example, if you start with this, you go to AX, then you go get AX. From X you go to, let's say, AX in one case, then you get AA, and then you go to B, let's say, so AAB, right? However, if I had started with AX and then I go to BX directly, and then I go to AX, then I will get ABA, right, and then
yeah.
ABAB. So that production of the grammar, the terminal string, or the string that you will get, it will be different. So it is like a instance, right? One instance produced from that grammar, that depends on the order, right? On the order of the derivation, right? So that will differ. However, the language, as you were asking, will not change, because once you have these sets of rules defined, right, that is enough for the language. So that is over. Like whatever possible strings it can generate has been described here,
Okay.
right? The derivation might change depending on the order, is what you need to be careful. Is
So
that
in,
fine?
in this production, this is called the production rules,
Rules.
right?
Yeah, yeah.
So in this production rules itself, the order doesn't matter. That's what
Yeah,
you're
yeah.
saying?
In this one it doesn't matter. Like the way we have written it, so it is X implies AX is
So
written
the
first.
sequence, what Afnan means to say, the sequence doesn't matter in which order we are writing the productions.
Yeah,
Okay.
So instead of the grammar 2, I can write 3. Instead of 3, I can write a 2. That does
right,
not
right.
matter.
Hmm.
So if you look at the things, we basically use some conventions. The things are written on the capital letters. Those are the variables, right? And small letters, those are the terminals. Those are the alphabets. So whenever we are generating a string can only have alphabets, right? The terminals only. So that's why what we do, we start with the starting variable. So here say s is the starting variable, and capital X, those are basically the non-terminals or variable. They has to be replaced by, gradually has to be replaced by all terminals, right? All alphabets. So that ultimately what we get, which is having only the alphabets, that small
Yeah.
case letters,
Everything is
that's
terminal here.
basically a string.
Hmm.
And the set of all possible string generated by the grammar creates the language, right? So it's a simple way. Whenever we talk about a English language, it's having a basic grammar, right? So from the
Yeah.
grammar, we can generate a number of sentences or strings. And each sentences, if I put all the sentences together, it's constitute my English language. The
Right.
same way, whenever we are defining a programming language also, so we have to first define the grammar behind it. So we basically define the grammar in terms of CFG. So there are another other ways also, but here we are studying CFG only. So in terms of CFG, so C kind of C++, all these grammars are basically a CFG grammars. So we can write the CFG like this, the productions. Now from these productions, we can actually generate all the syntaxes like for loop, if. So these are all generated by these grammars. So this is what is given. It's very simple. Like we can have A, B, right? We can have B, B. We can have A, B, B, right? So any string, it's any combination of A and B which ends with a B. I think that
Yeah,
is the
because after all
language
you
which
have to.
is accepted by
This one.
this grammar.
Yeah, because it has
So you
to.
need to understand that given a string, is it legal or it is validated by grammar or not, that you must understand. So that has to be done by these derivations. This below thing is a derivation. See changes in the arrow. In production, you are having just an arrow, but derivation having a imply symbol. So whenever I'm doing a derivation, we basically replace a variable with the right side of any production, right? So if you look at this s, the right side of s will be replacing it. If I look at x, the right side of any x production, right? So that can replace it. So you need to replace it so that you can get the string. If you cannot reach to the desired string or the sentence, so then that string is not validated. That's not part of
Yeah.
your language.
Right.
So actually in programming, no, this whenever the syntax checking happen, it's part of
Right.
compiler. It's nothing about the runtime exceptions.
So
So
can I
yeah.
can I just ask a question here? So is it possible to generate a string like A B A B through with this grammatical rules?
A,
A B A B.
yes, it's possible, right?
Yeah, it is possible.
Okay.
See,
So
you start with S, write a AX, right?
right.
Then replace the X with the third rule.
Third rule. Okay, and then go
So
back to the
you got
second.
A, B, X, then go for the second,
Okay.
then go for the fourth.
Yeah. So the order doesn't matter. That's what fundamentally I wanted to know. Yeah.
Yeah.
Okay.
The
Understood.
order in
Understood.
which we are describing these lines, right? This is not
Doesn't. Yeah.
important.
Right.
However,
Right.
the final thing that you're going to get depends on the order in which you had done the derivation, right? So
So
it is
actually, that is what happened whenever you put a program inside the compiler. So it just take whatever the lines, the syntaxes you wrote, and try to derive the syntax using these productions. If it can reach to your syntax, then it is approved. Otherwise, it's not approved. Something wrong. That's all.
Okay. So can we also convert this into a regular expression?
A few we can convert. Few
Okay.
we need to define verbally, like using an English term. All because a regular expression is a much more restricted grammar than a CFG. CFG is more flexible in that way. So basically, we are having different labels. So first is regular expression, then it's CFG, then it's context sensitive, I think, and last we are having that during kind of thing. So I cannot remember exactly the order, but the flexibility is more for CFG. So few of the CFGs can be converted into regular expression, but not all.
Okay.
Yeah.
Okay. Got it. Thanks.
all right. Shall we go ahead now?
Yes, Sapna.
Yeah, thank you. So that is what. So this other order doesn't matter, but the order in which we're deriving may change the string. So as you asked about the example of AB, that is also possible. So you start with S, you go to A, and then you go to B. Then you again come back to the second rule, and we don't have a numbering here, but we can refer it to as the second rule. Then we go to the last one, get ABA. So that is what it says. And lastly, the thing is that the language, again, as Arupsa mentioned, defined by the grammar G, written as L of G, is a set of all terminal, not that, all terminal strings that can be generated by G, right? So for example, it's a very good example of this one, let's say. So this grammar cannot generate the string A alone. That is not possible, right? Because you have to, it is necessary for you to end up in a terminal string. Then only you call it a complete production, right? So this is just a partial thing. You keep on replacing until you have something non-terminal here, right? So once you end at some place, then only you say that is terminal. That is the final string that is generated by this grammar. So similarly, we cannot have A, for example. Just A is not possible here because you must derive it. Therefore, it says the set of all terminal strings that can be generated by the grammar G. So that is the language. Okay, and these are the rules. So this must be clear. We'll go forward. So these are all the examples of derivations. Okay, again, so there is a slightly more compact way of.
Afnan.
Yes.
Hello. Sir. Can you give me a moment? I want to show something if you have some time.
Yeah, definitely, sir. Of course.
Just 1 minute, huh? Just
yeah.
I want to share something like a slide. Yeah. It's
sure,
basically an automata slide, but I want to show it
okay,
just to
okay,
get an idea, like
right,
how it's get replaced and all.
Definitely, you can share that.
Can you see my slide?
Yes, sir.
From the overlay. It's something like this. So I want to create a language, right? So these variables, VNs are basically the variables. So maybe I'm creating a basic English language using this. So I have sentence, noun, verb, adverb. So these are my alphabets, suppose. Ram, Sam, ate, sang, well, right? Now ace is the sentence, right? So these are my rules. Sentences, noun and verb, right? Then sentences could be noun, verb and adverb. And this noun could be Ram, noun could be Sam, verb could be ate, adverb could be, so this will be verb. It's my mistake. Adverb could be well. So I can basically derive different kind of string with this, right? If I want to say Ram sang well, right? If I want to derive this, so go to the sentence, maybe the second rule. This noun I'll replace with a Ram, the verb I'll replace with the sang, and the adverb I'll replace with will. So this is basically creates a kind of English simple sentence. And if you look at the type of languages, uh, so regular expression is the most restricted. So which is accepted by a machine called automata. Then beyond that you are having a context free. Then beyond that you are having context sensitive, and beyond that you are having unrestricted grammar. So Turing machine, which is for right. So if you look at the context, so whenever you are talking about the context free, so let me just tell you what is the context here. See, if you look at this kind of production, in left hand side you are having some variable which has to be replaced by the right hand side, right? Now if the left hand side along with the variables, if you have some terminals, those are called context. So on the left hand side here for A, this is called left context, this is called the right context. Now when it is a context free grammar, if the left hand side only will have a variable, no context. So that's why whatever grammar Apnan has shown you, you can see right side there are no terminals. Right side you are
Terminals,
having
yeah.
only variables. So that's why we call it as a context free. And
Do you,
most of the programming languages are based on this context free grammar.
do you mean left side, sir? I think you meant left side only, right?
Yeah, left side. I
Yeah,
told right.
I think it was right.
Okay, sorry. Yeah, left side. So
Uh,
left side, if you can see only the variable, that means it do not have any context.
right,
Neither left, neither nor right side.
right. Right side is what you get after producing, you know.
No, I'm saying for S,
Hmm.
there is no terminals on the left side or right side for S.
Oh, okay. For S, like, yeah. To the left
Uh,
of S, there is nothing. To the right of S, there is nothing.
So if it is a context sensitive, you should have something on the left or right of S.
Hmm.
Then it is a context sensitive.
Yeah, on the
Because
LHS side, right, sir?
on the LHS side.
Hmm. Makes sense. All
Yeah,
right.
Afnan, you can go on.
Yeah, thank you, sir. That
Okay.
was helpful, actually. So again, these are examples. Now, so what I was saying is that this is where the rules. Now, turns out that again, as we were mentioning, that we can mention certain grammars in the form of regular expressions also. Like, it is more compact way of writing the same thing. So if it is if we can convert it, then we can convert it. So for example, in this case, it turns out that the language that is defined by this grammar is can be described using this regular expression. So it is the same thing, right? So you have A and concatenated with A or B, and this whole thing star, and then we have B. So that is what this grammar is describing. Okay, so we can convert this. So it says in general how a context-free grammar looks like. So n is a finite set of non-terminal symbols, right? Because you can have something different also, which is not given here. So for example, if you have S that is implying A X here, for example, that's okay. Now you can also have another S or something else, different character that is going to somewhere else, like let's say Z, right? In the case of noun and adverbs, you've seen that, right? So it can have many non-terminal uh, symbols also. Need not be one only. In this case, we have only one, right? S, except for S, we have X, only. But we can have other things also, right? So therefore, it says that n is a finite set of non-terminal symbols in general. Like how do you define a grammar? Context-free grammar. So you can have a finite set of non-terminal symbols is a finite set of terminal symbols. Again, we go back to the alphabet, and therefore the the convention is the same. That is A. A is the alphabet. So it's a finite set of terminal symbols. That is what you're going to get finally. And S is a subset of non-terminal symbol. Is the start. You know. So from among the non-terminal symbol, the set of non-terminal symbols, S is kind of reserved for the start. Need not be always the case, but it is like the convention. Okay. And then P is the production. So the production is a finite subset of, recall that this is a finite subset of n cross n, n cross n union A star. So this is like the formal definition of how it goes. I mean, you can just derive it, but if you need, but that is what it's the set of productions or rules. Okay. And again, this is how we write it. uh, this is the syntax of writing. So this was the example. So we started with the example. Now we are describing it formally, how it looks like. So the production set is defined by this expression. That is okay. And the syntax to write it is like this. So there is a left hand side, there's a right hand side, and from the left hand side you kind of derive the right hand side. Okay. And in this case, since as Arup sir said, it is context free, therefore we don't have any terminal symbols in the LHS. Okay. So again, this is just discussing the same thing formally. What happens? Alpha derives beta in 0 or more steps, right? Like this. So first define, and then there's this inductive rule by which you keep following it, right? And if there exists uh, a possible gamma that from there you can go following that derivation rule n plus 1. If you can go there, then that's okay. If it does not exist again, then that will be invalid. Like basically it says that whatever string you generated, if you derive it using these rules, right, basically it is just following it inductively. Then whatever comes up at the end, the terminal thing, if it is if it can be produced, then that is part of that grammar. If you have something that cannot be produced, then of course it is not part of the grammar, and for that grammar it will be considered invalid. Okay. So that is how it works. And this is the formal L of G, right? So basically, W belonging to A star and all that. So these are all formal notation. That is okay. All right. Again, same example. So here you can see that in this case, the language that is defined by this grammar is turns out to be this. So A or B star, because again you can see that you can start from A from A, I mean like from the start you can either go to AXA or to BXB, right? And once you are at X, you can either go to AXA again or to BXB, and then finally you have to end up with a C. Okay. So this is what happens. However, I see that there is a problem here. Since we are ending with C, shouldn't it? Oh, right. So we are defining it like this, right? So we have a W where W is this A or B star, and then we have a C in between, and then we are having a WR also. I really don't know what WR stands for. Could you please uh, help us out, sir, on this one? What does WR stands for? Do you know that? WR.
Reverse of W. Reverse of W.
Oh, is it, sir?
String reverse.
Oh, is it? Okay, okay. So, but we are going to end up with a C also only, right? But then why are we having this?
No, C will be in the middle, right? So it's a A B C B A. Like
Oh,
this.
okay, because everything has this right side also, no? A, B.
Yeah, so
Okay.
it's a B A C A B A. Like whatever on the left of the C, that will be reversed on the right side of C.
Okay, okay. I think that will be a palindrome then in that case. I think so. Possibly. All right. Okay, I
Yeah,
got it.
kind.
Yeah, because it was in between, right? Okay, okay. I missed out on that. I'm sorry about that. So basically, wherever you go, these terminal symbols are fixed, right? So they are not changing. Therefore, everything is going to be in between only, because X is in between only of these two characters. And then you can finally have a C, but that is also going to be in between. And therefore, you're going to have C in the middle, right? And you have a set here, like a regular expression here, and that you concatenate with the reverse of that. And where this W is, corresponds to this A or B any number of times. So this is how we define it. We'll see some of the questions regarding this in the assignments also. That is why I was discussing this too. Yeah. Yeah, this one is again regarding this. So it says, although regular expressions are sometimes sufficient, a more expressive grammar is often used, such as the context-free grammar, right? Also, regular expression can themselves be written as grammars. That's okay. We'll deal with coverage criteria for grammars. So that is what. This is one example. Okay. Another example. So we have stream and then action, right? And then action. One or stream means one or more actions. Action could either be action G or action B. That is. Please read it as B. Okay. And so action G is going to be G, the literal, followed by S or S and N, where S is a digit, a 3-digit number, followed by N, that is also a 3-digit number. Okay, and then where N is like digit 2 times, concatenated with another digit 2 times, which is again concatenated with another digit 2 times, where digit could be either 0 or 1 to up to 9, right? So this is what it says. So some of the strings are this. So for example, G17. So it means we follow action G, and then we had S. So S goes to digit uh, okay, so it basically says 1 or 2 or 3, right? It need not be exactly 3. It says it could be digit, you know 2 digit or 3 digits. Okay, so therefore it says 17 here, or it could also be 1 digit. I think it says 1 is to 3, 1 to 3, right? Like 1-3 means it can be a 3-digit or a 2-digit or a 1-digit. So that is what it says, 17. And then herein you can see that it is directly 2, right? N, this is N, this part. So you say digit power 2 concatenated with digit power 2, and then again concatenated with digit power 2, which means 2 times. Okay, and I think this was the concatenation symbol. However, we are putting decimals here. Should not be the case. Should be 080190 only directly, because this is, I think, is the concatenation symbol, right? And one more possibility could be this, and so on and so forth. So that is what happens. Now these are the coverage criteria for grammars. Says terminal symbol coverage. It is all very easy to understand from the name itself. It says, whatever test requirement is going to be having every terminal symbol that is in your grammar, right? So that is TSC, terminal symbol coverage. Production coverage again says every production that you can have in the grammar. Or derivation coverage says every possible string that can be derived from the grammar. This one is like the difficult one, because sometimes it may happen that so many strings are possible. Then how can you have that? So it not always be possible. Yeah, that is what it says. Is in fact an impractical thing, because derivations are infinite for many useful grammars, and therefore you cannot do that. That is infeasible, but that is for completeness only. Most of the time we'll do either TSC or this one, PDC, production coverage, or terminal symbol coverage. So, and you can understand it from the name itself. So your test requirement would be covering for every terminal symbol that you have in your grammar. For the production coverage, you have to cover every production that is there in the grammar, which means the LHS and the RHS. So if it says production coverage, then every possible RHS you have to cover, right? So this coverage criteria considers generating strings that are member of the language generated by the grammar. In syntax-based testing, it is useful to generate strings that are not in the grammar too. Okay, and this is what we are going to do next in mutation testing, as in we will change it, or generate something which is not valid, and then we compare. We'll test on that and see if the output is as expected or not. So that is going to be the focus of the next lecture about mutation testing itself. Would that be okay if we'll cover that the next session, if possible? Or because I think time won't permit us to continue on this today. Will it be okay?
Yeah, that's okay, Afnan. But when you cover it during the next session, can you also cover the 10th week along with that, the Java part?
This one, right? Polymorphism and all this. Object-oriented testing, basically, right?
Yeah, because the reason I'm asking is, again, as Arup sir mentioned,
Hmm.
the lecture 2, I think, was talking only about the different possibility, different operators, right? I mean, you call it operators, correct?
Right.
But not exactly, none of the code was discussed.
Hmm.
So just wanted to see how it will look.
Right.
After maybe you can start with that infection propagation, that thing.
Right. So would it be okay if we do it in the next?
Yeah, that's fine. That's fine.
Alright. Yeah, sure. We'll. Your point is noted down, Anand. I will just try to cover with
So
examples.
Abnan, in between, like we want another day, or because
All
I
right.
think week 10 is coming, right?
Okay, so we can do Friday also, no? One session possible?
Friday evening, right?
Yeah, Friday at 8 possible.
Okay, I'll check out.
Yeah. In that case, it'll be easy because
Okay.
we can.
Otherwise, there is lot of content on 10. You
10,
cannot
yeah,
cover it up. Yeah.
yeah, exactly. So yeah,
Okay.
sure. We'll do one on Friday if possible, and then as usual on Tuesday. I think those two sessions will be sufficient to cover this one, the mutation testing part of it, and most
Okay.
of the week 10 content, if not all, but we'll try. We'll try to cover.
Okay.
Yeah.
Okay.
Yeah, sure.
Thanks.
Thank you, Anand. Yeah, thanks for the feedback. We'll see.
Sure.
Sure. All right. Thank you so much. I think we can stop.